Hey, what's up, guys? This is Chung here again. So this time, today's daily challenge problem, number 745, prefix and suffix search. Okay, so you're asked to design a special dictionary, right, which has like some words and allow you to search the words in it by both a prefix and a suffix. Right. So that's it, right? I mean, so basically you initialize like a word dictionary with a list of words, and then and you need to search by both the prefix and suffix, right? So for example, right, I mean, the word we have is apple, you know, and the prefix is prefix is a and the suffix is e. That's why we need to return the apple. Oh, and one more thing, and once we find like uh, a match, right? If there are like multiple matches we find, we need to return the one has the biggest index that of in the original words list. Okay, so going back here, so we have apple. So A and E, right? We can search because A is a prefix, E is a suffix. That's why we find this apple. So similarly for like, for AP, right? So if we have the AP as a prefix and the LE as a suffix, this one should also give us like the apple, right? And some like more like extreme examples, So this prefix and the suffix, they can be intersect with each other. So which means that if we add one more letters here, if the prefix is app, okay, let's do appe, right? And then the suffix is pple, right? This is a prefix, this is a suffix. So these two should also give us, sorry, this is appl, no, right? So this prefix and suffix should also give us like an apple, right? Cool. So that's basically the basic idea of this problem. And obviously, this one is like a try problem, right? Which means that we should use a try structure, the prefix tree, right, to solve this problem. And a naive approach is what? Since we have both a prefix and a suffix we need to match, then a naive approach is that we have to we need to build two prefix tree. One uh one is from the from start to the end, and the other one is from the end to the start. Okay, and then while building the prefix tree, right? We also gonna at each of the node, we're gonna maintain like a list or a set of the index of the word index that has that prefix. So the reason we need to maintain like a list of index or a set of index is because later on, after building both the prefix tree in the from left to right and from right to left, once we have this prefix and suffix, right? We're gonna use both the prefix and suffix to find like the candidates, right? The indexes has this kind of prefix where it's gonna be a list one, right? And then we're gonna find like another with the suffix. We're gonna find like a bunch of other index with a list two, right? And we want to find an intersect of this two list, and then among all of those kind of intersect, we find the biggest value, the biggest index. That's how we may basically solve this problem in a naive prefix tree solution, right? But as you guys can see, this one is not very efficient. Not only we need to maintain like two prefix tree, but also we have this intersect. Actually, that the prefix tree is not like a big issue. The bottleneck is like this intersect, because we might have like the words, right? So the words have like this 15,000. This two lists might be might be pretty big, and if we do intersect, it's going to be a n square time complexity, right? That's why we're hoping we can find like a better solution. Instead of like doing so that we can avoid doing this kind of intersect. So I mean, with this kind of prefix plus suffix problem, a common trick is that since if we like write two words, let's say we have apple, and if we have a like apple here, these two apples, we have if we have like anyway a separator in between, like a hash, like a pound sign here, if you look at this kind of two letters, from here to here, right? They're kind of like symmetric in a way that so this, let's say we have like a prefix like a and the suffix is e. So what does this one mean? It means that if you look at this one, so the e pound sign a, this is the string, right? Basically, if we have this string in the prefix tree, then we know, okay, so this suffix e pound sign a, it it it's a valid it's a valid combination for this apple, right? Similarly, if we have like ap, ap and what, this is a le, right? This one is also going to be a valid one. That's going to be what? Going to be the le plus this separator plus a and p, right? And if we continue doing this, let's keep this le the same, and then if we keep expanding the prefix tree, I'm sorry, the prefix going to be APPL and then LE, right? So this, like what we have discussed, this one should also give us like the apple, which in this case is what? So we have LE, and then the tag LE stays the same, and then we have the separator here, and then we have a APPL, right? So from here to here, right? So now I think you might have already find the pattern. So basically, how can we use like one prefix tree to cover all this kind of scenario? We just basically need to concatenate this apple, this word with this twice with separated by this pound sign here, and then we're gonna add a word into the prefix tree as what? As e pound APPLE, and then the second word is LE pound APPLE, right? The third one is the PLE, same thing, and then PPLE, same thing, and then last one APPLE, same. So now with this one apple, we're gonna add, instead of one word, we're gonna add this kind of 5 words into the prefix tree. Since with this kind of 5 words added into the prefix tree, basically we have covered all the possible prefix and suffix combination that's this word apple can ever have, because basically this e, right? So this e is one of the suffix, right? So this word, basically this one covers all the possible combinations, with the suffix as e, and the prefix could be anything. Prefix can be from a to apple, right? Because for this kind of word, when we add to the suffix tree, we're gonna add like e pound a, e pound ap, p and a, e pound apple, and if with this kind of e as a suffix, if the prefix is a, then we will look for this e pound a, and if the prefix is ap, and then we just keep going, right? We find the ap, okay, that's gonna be a another prefix, right, of this word, and then so on and so forth. So APPL, APPLE, basically, right? And similarly for this one. So basically, and then if we continue, basically the second word covers all the combinations with the suffix equals to LE, right? And then the prefix also the same from A to APPLE. And then so on and so forth. So the PLE is the suffix and the APPLE is also suffix, and so on and so forth. So now if we do this in this way, even though we're storing a little bit more, we get more like words into this kind of uh, prefix tree, but we don't need to do this kind of intersect, right? Yeah, and that's going to be a common trick for this kind of prefix and suffix solution. Actually, this kind of a trick can also be used. It's very common with prefix and suffix because, as you guys can see, if we concatenate this two words together, now if we look at starting from this kind of pound sign here, the left side is all the suffix, and the right side is all the prefix. Cool. And yeah, so let's start coding then, right? For the prefix tree, there are like a bunch of ways you can do it. Someone prefer using a dictionary. So to me personally, I maybe just my habit. I still prefer to create like a class, to represent the node in the tree. You can use your own way. Doesn't really matter. And self dot children, right? And then and one more thing, since we don't need to do this kind of intersect, and instead of storing a list of index for this prefix, we can simply store the max index for this for the same prefix node, right? And because since we're processing the words from the smallest index to the biggest one, we can always update this max index. Okay. All right, so to do this kind of root, so we have a node, right? That's going to be the root for everything. And for each of the word, since we need to use the index, I'm going to use enumerate, right, to the words. And what else? So here, there are a bunch of other ways you can enumerate those kind of new words we want to add. For me, I'm just using like this one. I'm creating a new word. It's going to be a word plus this one plus word, right? That's going to be the new word we're trying to add. And I'm starting from the first one. Basically we have apple, right? This one apple. I'm starting from this index, and I'll stop from here, right? So for each of the iterations, I will just loop through from this index to the end. That's going to be the string we're trying to add into this prefix tree. Okay. So it's for j in the range of length of word, right? This is the first level iterations. That's going to be the starting point of the new word, right? This is the starting point. And then, so for each of the new word, we're gonna do this kind of thing, right? So the current one is always equal to the root. And then, so this is the starting point of the new word. And then for each of the letters, I have a k in the range of this is the starting point of the new word, and we stop at the end of the new word. Okay, so that's why I create a new word here, because I want to use both of the length of the old word and the new word. Okay, and this character is going to be the new word of k, right? And then below it's just like the regular prefix tree template. So if c not in current dot children, right, we have current dot children dot c is going to be the node. Actually, you know what? So if we use like the a default dictionary here instead of like a regular curly brackets. Maybe we can remove this section, but I'll just keep it the way it is. I mean, to avoid this track here. But anyway, and then we have a current equals to current dot children dot c, right? And then current dot max index is going to be the I, right? That's how we update that. Oh, and by the way, I think in this case we don't need to consider this pound sign apple case, because in the constraints it says the prefix and suffix is at least one character. That's why this condition is not valid. All right. Yeah, I think that's it, right? So this is how we initiate the create this prefix tree, and then for the search, it's very simple, right? We start from the root, and then for the search word, we simply concatenate the suffix and the prefix, right? And then for the C in the search word, if C not in the current dot children, right, we simply return -1 because we know we couldn't find this combination. Otherwise, keep going, right? So once we have reached the end of the search word, we can simply return the current dot max index. Yep, I think that's it. Run the code. Did I? Oh, I think I'm missing like colon here. Okay, accept it. Cool. So yep, so it passed, right? So the time complexity for this one is what? Let's take a look. So first we have an n, right? So let's say the n is the length of the words, right? So we have to initiate, right? So to initiate this one, we have n times what? Times we have a nested for loop here. That's gonna be the what? This is gonna be the length of the words, right? So let's say we have the length of the words, basically the maximum length of the word is m. We have m squared, right? Because we have for loop to do that. And then for this kind of for the second part, which is a query, right? Plus what? Okay, so there are like this number of calls, right? To make the function. Of course, let's say this one is k. This one's k. K calls, right? So we have a k times what? Times a search word. This is the m, right? Because we simply have like a for loop here. And this one is like also within the boundaries of the maximum length, which is m. Yeah, so that's going to be the total time complexity. Right? And space complexity, of course, is the size of the prefix tree, which is what? Which is the n times m squared. Right? That's going to be exactly the size of this nested for loop here. Yep. So this is the space of this one. Oh. Cool. I think that's it, right? I mean, this is like a little bit of variation of a traditional prefix tree here, and here we basically we use a trick, to handle this prefix and suffix, right? By concatenating the word twice, and then we just add multiple words into the prefix tree to cover all the combinations of the prefix and suffix. Cool. I think I'll stop here, and thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.